Welcome to this lecture on single-photon nonlinearities in nanocavities, where quantum effects meet nanophotonics. At the nanoscale, a single photon can produce measurable nonlinear optical effects, something impossible at macroscopic scales. Let's begin by understanding why classical nonlinear optics requires extremely high light intensities. In conventional optics, nonlinear effects are extremely weak, because they involve high-order interactions between light and matter. The polarization of a material expands as a power series in the electric field, where Chi1 is linear, Chi2 gives second harmonic generation, and Chi3 gives third-order effects. For typical materials, the third-order susceptibility is about 10 to the minus 22 meters squared per volt squared. To observe nonlinear effects, we need electric fields corresponding to intensities of gigawatts per square centimeter, which requires powerful lasers. In conventional setups, we need many photons flowing through a large volume to accumulate enough nonlinear response. This raises an important question. Is it possible to achieve nonlinear effects with just a single photon? The answer is yes. By confining light to volumes much smaller than the cube of the wavelength, we can make single photons behave nonlinearly. The key to single-photon nonlinearity is extreme light confinement in nanocavities. The effective mode volume must be much smaller than the cube of the wavelength. Three main platforms can achieve this extreme confinement. First, photonic crystal nanocavities that use defect modes to trap light. Second, plasmonic nanocavities and nanogaps that use collective electron oscillations. And third, micropillar cavities that embed quantum dots for strong coupling. Here's a photonic crystal with a defect cavity in the center, where light is tightly confined. Let's calculate the mode volume for a realistic photonic crystal cavity. Consider telecom wavelength of 1550 nanometers. Lambda cubed equals approximately 3.7 times 10 to the minus 18 cubic meters. For a high Q photonic crystal cavity with refractive index around 3, the effective mode volume is roughly 6 times 10 to the minus 19 cubic meters. This is about 6 times smaller than the diffraction-limited volume, representing extreme confinement. Now let's understand why a single photon becomes significant in such small volumes. The energy of a single photon is h bar omega, which equals h bar times 2 pi c over lambda. For 1550 nanometer light, this gives approximately 1.28 times 10 to the minus 19 joules. This seems tiny, but watch what happens when we calculate the energy density. The energy density is the photon energy divided by the mode volume, giving roughly 0.2 joules per cubic meter. But for nonlinear optics, what matters is the electric field intensity. The intensity relates to the electric field squared through this expression. For a single photon, the electric field squared scales as h bar omega divided by the mode volume and permittivity. In nanocavities, a single photon can create electric fields of several megavolts per meter, enough for nonlinear interactions. At macro scales, a photon spreads over huge volumes. At nanoscales, it's compressed into tiny volumes, becoming like a hammer. To understand single-photon nonlinearity, we need the Jaynes-Cummings model from cavity quantum electrodynamics. The Jaynes-Cummings Hamiltonian describes a two-level atom coupled to a single cavity mode, with cavity frequency omega c, atomic frequency omega a, and coupling strength g. The coupling strength g determines how fast the atom and photon can exchange energy. The coupling g scales as the square root of cavity frequency divided by the mode volume times the atomic dipole moment d. Crucially, g is inversely proportional to the square root of the mode volume. Smaller volumes mean stronger coupling, which leads to observable single-photon effects. The Jaynes-Cummings model describes an atom and photon exchanging energy coherently in a cavity. For single-photon nonlinearity, we need the strong coupling regime of cavity QED. Strong coupling requires the coupling rate G to exceed both the cavity decay rate kappa and the atomic decay rate gamma. The cooperativity parameter quantifies how well we satisfy strong coupling. Cooperativity C equals G squared divided by kappa times gamma. We need cooperativity much greater than 1 for strong coupling. Let's calculate with realistic numbers for a state-of-the-art photonic crystal cavity. Coupling rate G over 2 pi equals about 20 gigahertz. Cavity decay rate kappa over 2 pi equals about 10 gigahertz. Atomic decay rate gamma over 2 pi equals about 1 gigahertz. This gives cooperativity of 40 well into the strong coupling regime. With cooperativity of 40, single-photon nonlinear effects become readily observable. One of the most striking single-photon nonlinearities is photon blockade. When one photon enters the cavity and couples to the atom, it shifts the cavity resonance, preventing a second photon from entering. The energy shift caused by one photon is approximately 2 grams squared divided by the detuning delta. This creates photon anti-bunching, where photons arrive one at a time rather than in bunches. The second-order correlation function G2 at 0 time delay becomes much less than 1, signaling strong anti-bunching. The first photon inside the cavity blocks the second photon from entering, like a bouncer at a club. How strong is this photon blockade effect in realistic systems? For an optimally driven system, G2 at 0 delay is approximately kappa over 4 grams, all squared. Using our example with kappa 10 GHz and G 20 GHz, we get G2 at 0 delay approximately 0.016. This is 60 times lower than Poisson light, with G2 equals 1, demonstrating strong non-classical behavior. Another remarkable effect is giant cross-phase modulation, where one photon shifts the phase of another. In conventional optical fibers, a single photon produces an immeasurably tiny phase shift on another beam. In a fiber, the phase shift per photon is about 10 to the minus 15 radians, completely negligible. But in nanocavities with strong atom-photon coupling, the situation changes dramatically. The phase shift per photon in a nanocavity scales as 2 grams squared divided by kappa times gamma. With our cooperativity of 40, this gives a phase shift of 80 radians per photon. That's a billion times larger than in a fiber, an enormous enhancement. A control photon in the cavity induces a giant phase shift on a probe beam passing through. This giant phase shift enables photonic quantum gates that operate with single photons, crucial for quantum computing. Plasmonic nanocavities achieve even tighter light confinement than dielectric cavities. Surface plasmons are collective oscillations of electrons at metal surfaces that can squeeze light into nanometer-scale gaps. Plasmonic mode volumes can reach 1/1000th of lambda over n cubed. Consider a 10 nanometer gap between gold nanoparticles at 800 nanometer wavelength. The mode volume is roughly 1,000 cubic nanometers, or 10 to the minus 21 cubic meters. This is 3,700 times smaller than the diffraction limit, representing extreme confinement. Two metal nanoparticles, separated by a nanoscale gap, create a plasmonic hotspot with extreme field enhancement. The trade-off is that plasmonic cavities have higher losses due to metal absorption, limiting their quality factors. Plasmonic quality factors are typically 10 to 100, much lower than photonic crystals, while photonic crystal cavities can achieve Q factors of 10,000 to 1,000,000. These single-photon nonlinearities enable practical quantum technologies. Single-photon switches can route photons using other photons as control signals. Deterministic single-photon sources enable secure quantum communication protocols. Photonic quantum gates built on these effects could enable all optical quantum computing. Quantum repeaters using photon blockade can extend the range of quantum networks. A nanocavity quantum gate where two input photons interact and produce entangled output states. Despite theoretical promise, experimental realization faces significant challenges. First challenge: positioning a quantum emitter at the exact location of maximum field in the nanocavity. Second challenge: matching the emission spectrum of the quantum emitter to the cavity resonance. Third challenge: most systems require cryogenic temperatures for quantum coherence, adding complexity. Recent progress includes deterministic placement of quantum dots in photonic crystal cavities with nanometer precision. The Lodal group achieved coupling rates of 23 GHz in 2020. Photon blockade has been demonstrated with 98% efficiency in several labs. The field is progressing from theory through fabrication and characterization toward practical applications. Let's compare the three main platforms for single-photon nonlinearity. Photonic crystals offer high-quality factors and moderate confinement with excellent integration potential. Typical Q around 100,000 and mode volumes around lambda over n cubed. Plasmonics provide ultra-tight confinement but suffer from lower Q due to metal losses. Q around 50, but volumes 1,000 times smaller than the diffraction limit. Micropillar cavities offer a good compromise with easier fabrication and integration with quantum dots. Q around 10,000 with mode volumes about 5 times lambda over n cubed. Each platform offers different trade-offs between confinement, quality factor, and fabrication complexity. Let's understand photon blockade more deeply through the concept of dressed states. When the atom and cavity are strongly coupled, they form hybrid dress states called polaritons. The energies of the dress states are omega c plus omega a over 2 plus or minus the square root of g squared plus delta squared over 4. The splitting between these states is the vacuum Rabi splitting, observable even with 0 photons. For n photons, the Rabi splitting is 2 grams times the square root of n plus 1. For 0 photons, the Rabi splitting is 2 grams, demonstrating quantum vacuum fluctuations. For 1 photon, it increases to 2 grams times root 2. The energy ladder shows how the Rabi splitting changes with photon number, creating anharmonicity. This photon number-dependent splitting creates anharmonicity that prevents resonant absorption of a second photon. These effects represent true quantum nonlinearity operating at the single quantum level. Classical nonlinearity operates in the high-intensity regime where the field is strong and can be treated classically. Quantum nonlinearity operates where individual quanta matter, and there is no classical analog. Classical third-order nonlinearity gives chi 3 times e squared times e. Quantum nonlinearity is fundamentally described by operators coupling photons and atoms. The quantum case fundamentally cannot be derived from classical electrodynamics because it involves discrete energy levels. How do we experimentally measure these quantum nonlinear effects? We measure them through photon correlation measurements and high-resolution spectroscopy. A Hanbury-Brown twist setup with 2 detectors measures the second-order correlation function. G2 of 0 equals the coincidence detection rate divided by the accidental rate expected for independent photons. A Hanbury-Brown twist setup measures photon correlations, revealing quantum nonlinearity. In conclusion, single-photon nonlinearities and nanocavities open new avenues for quantum technology.